Okay, welcome to 11th lecture of stability of structure. So, what we are discussing is lateral torsion buckling of beam. So, that involve both the flexure as well as torsion. So, we have derived the formula for the moment, critical moment. So, this is the critical moment. Okay, this is the critical moment for the at which lateral buckling occurs for the beam. So, we have assumed the beam I section beam to be subjected to pure bending moment and then M. Okay. So, that expression is similar to the expression that you see in various standard, okay, for design. When you design laterally unrestrained unrestrained flange, top flange especially, which is under compression, right. So, of course, if there is a gradient in the bending moment diagram, bending moment diagram is varying, and then there will be some modification to that. Okay. So, we have derived that, we have seen that how we have derived the potential energy function. Potential energy functional has strain energy and work done, and there was little consideration in finding out the end rotation that is happening, end rotation of the two end, right, subjected to out of plane bending, bending, lateral bending. Okay. So, bending was happening in the basically xy plane, that means with respect to z axis, right here. Now, you see that for rectangular section and others, for solid section or for closed section, okay, for solid and closed section, what I mentioned that the warping constant is very small. Okay, warping constant is very small, it's tending to 0 nearly. Okay, and then this M is critical moment. M critical can be simplified as pi by L root. So, there is no warping. So, E I Z and G. So, okay, so it is only flexural stiffness as well as stiffness, Sandwin and torsion, torsional constant. Okay, this is the. So, for a rectangular section, actually this can be derived in a much simpler way that I can show you a little bit. Okay. So, for example, if you consider you consider a slender kind of so this kind of rectangular section and then you define your coordinate system the way we have defined x, y, z. Similarly, x, y, and I think we are defining z, right. Then how we will arrive at that I am showing. So, when other end maybe it is whatever fixed, whatever is happening. So, here you see this is going to it will be twisted, right. So, you see that the way it will deform, this end will be twisted. So, maybe it is going to say the deformed configuration is being like this, okay, something like this. So, it is essentially happening like this, and then something like this, you see that, okay, due to lateral buckling. Then what will happen? So, I am considering that it is also subjected to pure moment. Okay. So, the pure moment with respect to x axis. Okay. So, pure moment with respect to x axis. So, pure moment bending moment. So, M x x, okay, with respect to x axis. So, now x, y, z, this is going to deform, and this is going to have, I am considering that this being x dot, this is being y dot, and then this is being z dot. So, z dot and z is say parallel, z and z dot will be parallel. So, that is not a problem, but there will be some change, So, from x y it is happening like that it is it is coming to be x dot, y dot, and okay. So please note that this bending moment I am denoting, so using arrow diagram, so mxx, okay, arrow diagram, because if it is, the S screw is going to come like that, so okay, so I am just denoting this is as mx, okay. So if they are getting twisted, that means this angle is beta and this angle is also beta, right. So if this angle, so then it will have two component, mx dot is going to be mx cosine of beta, and beta we are considering in very small deformation. So mx cosine beta means mx, beta tending to 0. So essentially mx, right. And then what is happening that here this moment, that moment is my dot is going to happen. So mx, sine of beta. So mx sine beta means mx into sine beta is equal to beta. Okay, fine, right. Now, so that I am just considering the component. Now, if I consider the component, so this is in xy plane. Xy plane means, this, transverse cross section. Okay. If I consider in xz, what is happening? Xz is after deformation, xz is coming to x dot z dot, right? So it is horizontal. So here it is x, and here it is z. It was in horizontal plane. It is coming in x dot. So x dot and z dot. That is happening basically here. I am going to consider this one to be x dot, and here is going to come, it is z dot. Okay. Now, see this, the on the vertical plane the section is undergoing twist, right? But here in the xz plane, this is going to lateral bending. This is beta, this is because it is twisting is happening in this vertical plane, right? Twisting, right? But here what is happening? Here what is happening is bending, right? In the horizontal plane, bending in the xz plane. So bending with respect to what? Bending with respect to z axis, right? Sorry, not with respect to z axis, with respect to y axis, right? So this, now if I consider the deflection along x is EU, deflection along x, EU VW, right? Then what is this? This is nothing but del U del Z, right? I am considering that because of flexure there will be deflection along x, right? So EU VW are the component, right? Along x the EU, along V this is V, and W is fine, U and V. So when it is deflecting, when the flexural deflection happening in xz plane, bending is happening, that with respect to y axis, the deflection is along y. So this angle is nothing but what? Du dz, right? So now this bending moment mx, the component of this along axis is what? This one is mx dot is nothing but mx, cosine of du dz, and cosine of du dz, it is very small, so mx, right? And what about this component? This one is mz dot. Mz dot is nothing but mx, cosine of pi by 2. This angle is pi by 2 plus pi by 2 plus du dz. So pi by 2 plus du dz means minus mx sine du dz, right? Du dz, and that means it is minus x du dz, minus x dz, right? Now, so you see, so even in the deformed configuration, when x is coming to x dot, mx dot is not going to change. Mx dot is mx. Mx dot is mx in both the cases, right? Because there is a common x axis, x dot axis, right? But what is happening is that in there is a twisting moment that is coming, okay? That there is a there is this moment, my dot is coming mx into beta, right? And then we are having another thing, twisting moment that is coming, which is mx du dz, right? Okay. So now we can write down. So there are three moments, you know, mx dot, my dot and mz dot. So mx dot is nothing but the bending moment with respect to x axis, right? So, so E I with respect to x axis, so that means, you know, it is xx, you know, xx, you know, d2v dz2 is happening, it is nothing but mx, that's what I am going to write, right? And then E I y y, that is d2u dz2 is going to be E u d2 that is with respect to y, right, my dot, right, and j, then there is only Saint-Venant torsion del u d beta, nothing but mz dot or mz, okay. These are the three things happening. See, mx dot is the bending moment with respect to x axis, right? So that is causing bending with, you know, with respect to x axis. Bending moment y dot is going to cause bending moment with respect to y axis. That means it is going to cause lateral. So this is, you know, vertical bending, bending in vertical plane, vertical bending in vertical plane. This is, you know, lateral bending, lateral bending, and this is, you know, that, you know, Saint-Venant torsion, right? See, right? Now I will just substitute mx dot is this is always x, right? My dot is what? My dot is mx into beta, right? Mx into beta, and mz is nothing but minus mx du dz, right? So now I will just remove this. I am removing this one. Now you see, we don't care about the bending in the vertical plane. We don't care about the bending in the vertical plane because this is already for in equilibrium, right? Equilibrium, and this is not contributing to lateral stability, not contributing to lateral buckling, right? Lateral buckling or instability. This is not contributing, right? So you just, but these two you have to consider. Now you see there is a coupling, okay. So what is going to write? You write d2u dz2 is mx beta, and gj, you know, d beta dz into minus mx du dz. So here what I will do now, so du dz, if you differentiate these twice, right, so what is going to happen? So I will combine these two, okay. So combining, I am going to combining, combining what I can write, E I y d2 dz2 is nothing but minus gj by mx, you know, d2. See, because this is beta beta, so I can eliminate u from these two expressions. Look, this is in terms of beta beta, okay, we and only eliminate this. So this is my ey, and then minus gj by mx, and d2 beta d2 beta dz2 is equal to mx into beta, okay, right? Now you may wonder why I am not considering warping. Yeah, I have already mentioned that, right? So you see that this way, through equilibrium approach, you can also find out. We have deformed it. We are considering equilibrium approach. You have deformed it, and then we are writing down equilibrium equation. We are not using energy approach, right? So this is an alternate for you know, way to derive the lateral fraction buckling as well. Okay. Now this one equation can solve a very, you know, d2 beta dz2, you know, plus, you know, plus mx square, eiy zj beta is equal to 0, and this one if we denote as k square or lambda, this one I can define as lambda square. So lambda square is mx square divided by e iy zj. So d2 beta dz2 plus lambda square beta is equal to 0. And now we can find put the boundary conditions that at x is equal to 0 and at x is equal to L, both the end, a boundary condition in a way. So beta is equal to 0 and d2 beta dz2 to be 0. So beta is equal to 0 means it is restrained against twisting and it is unrestrained against warping. We are allowing it to warp freely. That lead to this equation, right? This boundary condition. So now may I remove this one? All of you have noted down this one I am removing it, okay? So if you solve it, then if you solve this second order equations, it will be nothing but a, cosine of lambda z, plus b sine of lambda z, right? So and then d2 beta dz2 is nothing but minus a lambda square cosine lambda z plus this will be sine will be cos, and then here it will be minus b lambda square sine of lambda z, right? So you see that if you substitute beta is equal to 0, beta is equal to 0 at z is equal to 0, sorry, this is not x, it's z, right? Z. So z is equal to 0 into 1 plus b. So a is basically 0, and then this one if you substitute 0 is equal to minus b lambda square sine lambda L, sine lambda L, and then this one is lambda L. So that means sine lambda L must be is equal to 0 and sine pi, okay? So lambda L is equal to pi, and then lambda square L square is equal to pi square. So for lambda, what is lambda square? mx square divided by e iy gj is equal to pi square upon L square, or mx critical moment is nothing but pi by L root e iy. This see that we same thing, only centimeter and torsional constant is there, and flexure friction, lateral torsional, lateral flexural buckling, right, critical, right? So you see how we are finding it out, right? So that is the way you solve it, So this is an alternative approach to do this. So in summary, what we have learned that we started. So this in the second chapter. So first chapter we have covered all the idealized system, toy system, and we have demonstrated all the basic behavior, stability behavior, they individually, all possible mode or in combination, those are portrayed by elastic system. And in the second chapter we have considered the beam, beam column system. We have seen how it is leading to amplification of, deflection and moment, and other quantity as well. And then we have, considered that, it's since we are all aware about how to find out the buckling, how to find out the buckling load for the column, that we have done in our undergraduate, right, by solving the differential equation, of equilibrium, the deformed configuration, and then solving it, we have obtained the eigenvalue problem, but trigonometric eigenvalue problem, right? Trigonometric, why? Because it leads to a transcendental equation, right? Okay. And then we have considered the elastica, finite deformation of column, to demonstrate that column hardly has any post buckling post critical strain, and then we have demonstrated the behavior by considering the where that flexure and torsion are coupled. So we have considered the torsional flexural buckling of column, and we have considered lateral buckling of beam. Those were, I mean, very close to our heart, to civil engineers at least, because we have seen this formula. We have used this formula while designing steel structure, right? And it is also, I think, very much useful for aerospace structure design as well. Okay. And we have seen that for solid section and closed section, because we have a very, very low, warping rigidity, the warping is very, very negligible over there, and we do not require to consider it. For solid section and closed section, in closed section J is what? When, okay, 4L square integration ds by t, okay, those are Sven constant, but warping constant is different, okay. So for I section, warping constant is find out as IF h square by 2, right? IF is that you have seen, right? So it basically depends on the sectional area of the flange as well as the distance between the two. Okay. Anyway, so we have covered that. Okay. So now we are going to start a third chapter, and it is a very simple chapter where we are going to demonstrate that how we can use finite element for the finding out the critical load. So we have all learned about numerical method, that matrix method or finite element, little advanced finite element method for structural analysis. So we will show that with a simple example for the beam column example, how to derive the, how to convert the eigenvalue problems in terms of matrix formulation, finite element formulation. So essentially geometry, whatever the eigenvalue problem we are solving, that can be either in for the closed form solution, which is leading to a trigonometric eigenvalue problem, that can be converted into a algebraic eigenvalue problem through discretization, because the differential equation is essentially being discretized when we are doing in finite element, right, or matrix method, right. So that is what I am going to demonstrate. Now, although I am demonstrating only for the column, but please note that the approach is general, and since all of you have kind of exposed to finite element course, so this approach can well be extended to all kind of buckling analysis, be it buckling of plate, buckling of cell, buckling of any other structure, frame, things, right. Okay. So that is what I am going to demonstrate to you. So many of you know finite element, I am going to follow the same thing. Okay. So there are two distinct approaches. One is of course based on energy formulation, right. We can go from potential minimization of potential energy, or we can follow the Galerkin approach. Galerkin means Bobnam-Galerkin. Okay. So I will try both actually. Okay. So just to demonstrate that, and this chapter is very simple. Okay. So you see how we are going to do. So you have learned that in matrix method or finite, for example, there is this column. Okay, right. Okay. So we want to find out the buckling load P for this. We know the closed form solution for that. Either we can discretize it into finite element, right, or in matrix, right. So we know how to. So we can discretize using beam column element. These are defined as node 1, 2, 3 node, and these are defined as element, right. And we have this nodal connectivity, right. Now same thing, that is more even. This is more important for frame structure, because sometimes you will see, although for beam column it is easy, for plate and cell also we derive the governing equation, but for the frame it is difficult to have one single differential equation, right. So it is most handy for the frame. So for example, it is subjected to some critical load P. You want to find what is the value of P, so that these two column buckles, okay, this is length L, less and length L. So for the analysis of frame, right. Then also you will sometimes you will see, say you are having this kind of say space stresses, right. So there is some load P is being applied, so you can find out what is the critical value of P, so that so for the frame and this frame, be it space frame or be two-dimensional frame, okay, the best method to analyze for the critical load, and it is of course there is possibility that some members will be under compression, right, because we are considering the buckling as the only form of instability as of now, right. So, for this problem it is easy to use the matrix method or finite element method for the analysis of stability, which will result eventually the resulting eigenvalue problem will be solved as a algebraic eigenvalue problem, because the differential equation is basically will be converted into algebraic equation, sets of algebraic equation, okay, linear simultaneous equations, right. Of course, if you want to do post buckling strength, if you want to analyze for post buckling, reserve, then you have to do a full nonlinear analysis, geometric nonlinear analysis, okay. That is discussed, that is the subject matter of a nonlinear finite element course, that I am not going to discuss it here, okay, fine, okay. So, as we see in any matrix method or any finite element method, so for example, you are having a you are having a frame structure, you are having a frame structure, or you are having some kind of structures, these are all hinge, and it is subjected to some force P. So, the first thing to do is to discretize the structure. So, we define node here, right, we are discretizing. So, these are node 1, node 2, node 3, node 4, and then there is global nodal connectivity. So, element connectivity. So, member 1 is connected between 1 and 2, member 2 is connected between 2 and 3, member 3 is connected between 3 and 4. In finite element literature, we call them as element, finite element, right. So, finite element 1, and this element is a beam column element, right. Here also similarly you can discretize it, node 1, node 2, node 3, node 4, and then these are element 1 connected between node 1 and node 2, element 2 is connected between node 1 and node 3, element 3 is connected between node 1 and node 4. Similarly, when you for a plate element also, when we will do the buckling of plate, you will see that we can discretize it using finite element. So, here you can use a 4 noded element, or there can be higher order element, 8 noded element, 9 noded element, things like that. Similarly, for cell as well, cell element also you can have, of course, this will have curvilinear coordinate, right, and then you will see that you can have this node. So, before doing that, since all of you are already exposed, we have to find out the element level matrix, the stiffness matrix for the element, each element, right, and then we have to assemble them to form the global stiffness. All of you are aware about the global assembly, element level assembly, to form the structural stiffness matrix, right. So, the first we will see that we will try to derive the matrices at the element level, which are required to solve for the finding out the critical load, okay. We are not considering the post buckling strength, we are considering the how to find out the critical load for buckling, okay. So, for that we are going to consider, so here is let us consider and a beam column element. I am considering beam column element because unless and until you have out of plane deflection, you cannot analyze for buckling. So, only a pure truss element, if you have a truss element, if you only have axial degrees of freedom, it will not be, you cannot analyze for its buckling. You have to allow for out of plane deflection. So, you have to essentially, formulate it in terms of a beam element, you understand. So, I am terming it as beam column element. So, it has 2 node and this is a beam column element, beam column element, beam column element, okay. So, when we are considering the beam column element, what we are trying to find out? We want to find out stiffness matrix, right. So, we are going to follow the procedure. There is a simple procedure to find out the stiffness matrix following the, when we write down the, stiffness matrix, it is basically F is equal to K into delta, right. This kind of matrix form it will come, right. So, Fi is essentially Kij into delta J, right. So, Kij is nothing but force developed at node I due to unit deformation at J, right. So, for a simple beam we can restrain all other degree of freedom, we can give unit deformation here and we can find out for what is the force or moment developed, then we can find out the stiffness matrix, right. term for the stiffness matrix, right? That is very simple. That's what we did in our undergraduate. But here I will not do that. Why? Because I want to emphasize the formulation of finite element once more. I want to make it general so that it can be followed for the plate as well as cell and all other things, okay? Fine. So I will do finite element, not like this ad hoc way to find and determine the stiffness. Okay, so in finite element, what is the way? We are going to follow the displacement based finite element, right? Almost displacement finite element, displacement based. Now, are you aware that there are alternate formulation finite element? All of you are aware that why only displacement we are considering? There are another stress based finite element, there are mixed formulation. Are you aware? You did finite element, all of you, right? You know stress finite element? No? You are not even aware why you use displacement based finite element over stress based? No? Because displacement finite element formulation is very general. It can, if you learn for one, it can be direct, easily extended to the other, okay? But stress based you require some special input from its behavior and others, okay? But stress based finite element was pioneered by THHP from MIT, okay? It was also a vast literature is there, and there is an advantage on stress based. Sometimes in nonlinear analysis, the tangent stiffness matrix can be obtained in closed form in stress based, but we are not talking about those stuff, okay? So, what if displacement, then what are the degrees of freedom? We are not y and z. The degrees of freedom, of course, here is vertical deflection and then rotation, deflection and then rotation, right? Okay. So, W1 theta 1, W2 theta 2, right? So, W1 theta 1, W2 theta 2. 2 deflection and 2 rotation, right? Fine. Now, we are going to consider simple. We are not going to consider shear deformation. We are going to consider Euler-Bernoulli bending. But all of you are aware about the importance of shear deformation, right? We are not considering importance of shear deformation, okay? We are going to see only Euler-Bernoulli beam bending, okay? So then what is going to happen? So then we can essentially write theta can be expressed as theta is nothing but dw dx. That is possible, right? Because plane section remain plane before and after deformation, right? Theta is equal to del w del x. We don't have additional shear deformation, right? So the first step is interpolation of the displacement field, right? So what is the displacement field W? W is the displacement. So I am writing W displacement field. I can express that. How many constant I know? W1 theta 1, W2 theta 2, 4. So we can evaluate at the maximum 4 constant, right? So may I write alpha 0 plus alpha 1x plus alpha 2 x square plus alpha 3 x cube, right? 4. Then I am going to put at x is equal to 0, W is equal to 0, at x is equal to 0, W is equal to W1, theta is equal to theta 1, and x is equal to L, W is equal to W2, x is equal to L, theta is equal to theta 2. This we are going to do. So here, it is alpha 1 plus alpha 2 2x plus alpha 3 3x square. So x0 W is equal to W1, x is equal to 0. So alpha 0, this is first equation, and theta is equal to theta 1, theta 1, and x is equal to 0, alpha 1, then W2, theta 2, so now we can solve for, we have 4 equation and 4 unknown, we can solve for W1 theta alpha 0 or solve for alpha 0, alpha 1, alpha 2 and alpha 3. These are constant, right? These are constant. Okay. So, these can be, so we can write W is equal to we can write W is equal to, if we solve it, then you will see W is equal to alpha 1 is nothing but 1 minus 3 x square by L square, well, let me write it. Right. So, you see that we can write N1 W1 plus N2 theta 1 plus N3 W2 plus N4 theta 2, right? N1, N2, N3, N4. This is N1, right? This is N1. This is N2. This is N3. And this is N4, right? Right? And what are these are called? N1, N2, N3, N4. These are called shape functions, right? Why they are called shape functions? Because they basically shape functions because they help in interpolating the from discrete they help in interpolating this nodal displacement to the displacement field inside the element, right? So that's why they are shape functions, and they have some property, right? These shape functions are called Hermitian shape function because they are Hermitian shape function because they are Hermite polynomial, right? Because of they are Hermite polynomial and they have some some characteristics. Okay, they also for certain different class of differential equation they form a legitimate basis. Okay, so anyway, so we can if you want we can draw it. N1 will be something like this. So it is no slope, but its value 1, 1 minus this 1 minus 3 x square upon L square plus 2 x cube upon L cube. And N2, for N2 it is different. You cannot plot directly N2, but you have to plot N2 dot, derivative of N2. Okay. So then if you plot derivative of N2, x minus 2 x square by L plus x cube by L square, derivative of that. Why derivative? Because W is related to theta 1. So dW. Okay, so then if you take the derivative, then you will see that it will have. So here it will have a 1 value of 1, slope is 1. And then similarly other two shape function you can plot, other will also look like this, So at node 1, node 1 they are 1 and elsewhere these are all 0, okay. Here it is, you see that N1, N2, N3, and then if you plot N4 also. So this property is called shape functions has some property, you know, it is its value for the displacement, it value takes 1 at that node, elsewhere it is 0. So, this is called Kronecker delta property. Okay. So, Ni Nj is delta Ij is Kronecker delta. Okay. This is called Kronecker delta property. Okay. And then if you sum them up, the shape function at any point, it will sum up to a value of 1, because it is interpolation function, that is the reason. Okay. And another thing is that Hermitian shape function, any shape function, all of you know that perhaps, that they must have they must be complete polynomial. That means you have to first you know, you have to have this constant term, okay, and then you will have this first term, okay, and then second order term and things like that. You cannot arbitrarily. So, you know, so in one dimension it should be 1 x square, this all these terms should be there in the point, okay, and in 2 dimension it must have a 1 x y, then x square x y square some. So, if you want to have 3 term, it is like that. If you want to have 4 term, then it should be like that. So, this is called Pascal triangle. Okay. So, you must have, so it must be complete polynomial, it must, okay, have some constant term to allow for the rigid body mode and thing. I will discuss more. Rigid body mode is very important in terms of the geometric stiffness matrix, you will see. Okay. Now, so we have interpolated displacement field using shape functions, right? Now, everything is very simple now. So, may I remove these things? All of you know these things, I am just refreshing and brush up your little knowledge on finite element. Okay. So, let us remove it. Okay. So, then what we are writing that, you know, W is nothing but, you know, I can write N into delta, N is N1, N2, Nt, N3, and delta is W1 theta 1, W2 theta 2, right? Fine. Now, once you are having, so you see that in nodal, so a discrete values are converted into continuous field, displacement field. So, that is the basically role of the shape function. So, for any element, that is what it does. So, now I will see that I will go to the strain energy function. Strain energy function is what? Pi, you know, potential minus work done, right? Sorry. So, potential energy is strain energy minus work done. So, for this one, it is Ei upon 2 integration 0 to L, you know, d2w dx2 square dx, and what is work done? Minus p by 2 integration 0 to L dw dx square dx, right? I can have other, you know, load vector etc. that I am not considering as of now. If you want to consider for the load, you can definitely consider, you know, my integration 0 to L, you know, qx dx, you know, qx wx dx, no problem for the load vector. Not considering that, you know how that is resulting to consistent load vector and things like that. Now, I am going to consider only these two. Okay. So, now, so then I am going to write it Ei by 2 integration 0 to L. What I will do, if W is like this, then from here you see that W d2W d2, so d2W dx2, you know, d2W dx2 is d2n dx2 like this, right? So, may I write it like this? So, right? Yeah, is that fine? Because what I have to, why I am taking d2w dx2, I am basically, you have to ultimately result into a square. So, you have to have the conformity in the multiplication term, right? So, that is what delta transpose d2 dw dx into dw dx. This one I am just taking transpose, so that it becomes, so this is a row vector, this is a column vector, right? So, ultimately these two will be a column vector and these two will row vector, right? So, that is what I am doing, okay? Fine? Okay, now integration dx. Now, what this is, this what we are getting, So, this one similarly we are going to write load vector you can put it, but it's not required as of now. I mean, that how to do, if you integration 0 to L, if you want to put this Qx, I am writing Qx, and then this one is in Wxn transpose delta dx. Okay. Now, we always try to minimize the potential energy, right? So, what I am going to do? I am going to minimize del pi. What is my nodal displacement? Delta, right? Just delta modal. So, how differentiating, there are 2. So, 2 will cancel out, delta square, delta transpose delta. So, it will be 2 delta, 2 will be cancelled out, integration 0 to L Ei, and here I am going to write this one because this is a row vector. So, n double dot and special derivative I am taking double dot, okay, and this I am going to write n double dot dx minus here also 2 will cancel out, p integration 0 to L this equal to 0, energy minimization. Okay. You have done finite element, huh? All of you noted it, huh? Okay, now which term? Yeah, delta term will be there, all right. Delta term, one delta term will be there, delta term will be there, yeah. Here, here there will be no delta, yes. Ultimately, so what we obtain? Now, what is this term? All of you know. This is what? This is the stiffness matrix for the conventional stiffness matrix for the beam, right? Conventional stiffness matrix for the beam, right? So, I can write this is K. What is this term? Load vector, right? Load vector, right? I can write it to be, Q or whatever, load vector P maybe, and then, delta is there, okay. What about this term, new term, which is coming due to work done by the, von Karman nonlinear and axial force, P, the function of the axial force, and then the, this matrix is nothing called geometric stiffness matrix. Geometric stiffness matrix. Why it is called geometric? Because it depends only on the L and P, length of the member as well as axial force P. It's a function of the phi. You see that? It is also called stress stiffness matrix. Okay, initial stress stiffness, because it depends. It is a value of the stress in axial force, whatever is there. So all of you know what are the terms of K. K I am not I am writing. So K is basically double derivative and do the integration so you will get the term so these terms I am writing to you so EI by L cube I am EI flex by L cube and here it is 12 6L minus 12 6L and 6L 4L square minus 6L 2L square minus 12 minus 6L 12 minus 6L 6L 2L square minus 6L 4L square. So, it is a function of flexure rigidity and this is the stiffness matrix which is depends on the flexure stiffness length all this. And this new a kg, this geometric stiffness I am just writing geometric stiffness, this will be P by 30L 36 3L minus 36 3L 3L 4L square minus 3L minus L square minus 36 minus 3L 36 minus 3L 3L L square minus 3L 4L square. And P, P, see either you can have consistent load vector or you can have lambda load vector, okay. It is not for static analysis, you know that, but for if there is no external load, this will be 0 and that is basically resulting into eigenvalue problem, right. So, the eigenvalue problem, so you see that, so this is basically the eigenvalue problem is given by K plus Kg delta is equal to 0. This is the eigenvalue problem, algebraic eigenvalue problem. Eigenvalue. And if you find out the eigenvalues, that eigenvalues will give you the value of P and the P critical, right? The eigenvalue. So, there will be a number of eigenvalues and the lowest eigenvalue is basically the lowest critical load, and there since there is a number of eigenvalue, higher eigenvalue is given of the will give you the higher modes, okay. The way you have solved the eigenvalue problem for the free vibration problem in structural dynamics, right, that involves the stiffness matrix and the mass matrix, but that was generalized eigenvalue problem. So, K phi is equal to lambda omega square AMP, that, but here it is a not generalized, it is an eigenvalue problem, right. And instead of mass matrix, here the role of mass matrix is basically taken by the geometric stiffness matrix, okay. And this geometric stiffness matrix is a function of P, and from where so that is what it is related to the eigenvalue eigenvalues. So, lambda will give you the critical load, you see. So, finding out the eigenvalue problem finding out the critical load for a beam column frame, a plate, a cell, anything, is basically leading to a eigenvalue problem. And when it is leading to eigenvalue problem, please note that this is a linearized, analysis. That means we are not giving the, we are neglecting the higher order terms, non-linear terms. When it is eigenvalue problem, still the linearized system. You see that. Nevertheless, please note that von Karman nonlinear terms are present here. When we are finding out the geometric stiffness matrix, its origin is heading into nonlinearity, because we are considering a part of the geometric nonlinear term. So, if you see epsilon xx is basically du dx plus half du dx square plus dv dx square plus dw dx square uvw, right. Now, for the, this what is happening, d dx of u is nothing but, u is what? U is nothing but dw dx into, theta into z, right, theta into z, and theta is nothing but, please note that u for the bending, u is what? Z into theta, and z is nothing but, theta is not dw dx into z, right? You see, and other bond curve. So here it is coming epsilon xx is coming as, if you just take it, z, d2w dx2, and from here if you take half, out of plane deflection, here is dw dx square. So this term is contributing to bending, whether this term, and this is linear, but this is non-linear, it is happening dw dx square. Other terms are dropped because this will be negligible, right, this and this. So the origin of the geometric stiffness matrix lies into non-linearity, but it is not capturing the fully geometric non-linear. It is a part of geometric non-linear that we are capturing, at least as far as, at least for this beam formulation, right. Of course, we can have a generalized formulation for the geometric stiffness. We consider all the term. If you consider 3D, maybe, you consider a dam, 3D body, and maybe it is subjected from the both the end, it is subjected to some compression, it is coming like the way folded mountains are formed. Okay, similarly, maybe if you are considering a case, you have a 3D dam, and in both end, maybe there is movement of mountain and things, and it is being compressed. So you see the folded mountain will be formed, right? Geologic material folded, but here there will be maybe, and then you may consider that while, a 3D that this will buckle, okay. So 3D formulation, all these component will come, okay. So we must now, you will see that geometric stiffness matrix, since its origin is hidden into geometric nonlinearity, but please note that when you will do full geometric nonlinear analysis, if you do a nonlinear fundamental element course, geometric stiffness matrix will also be a part of the tangent stiffness matrix, but not all. Please note that tangent stiffness matrix, one part of the tangent stiffness matrix will be, will be contributed, geometric stiffness matrix will contribute in the nonlinear and the tangent stiffness matrix, but that is not, there will be additional contribution from nonlinear strain term, Green Lagrange strain term. All of you did Green Lagrange. When I am writing this, it is Green Lagrange strain, right? Now, so if I want to solve a simple, I will solve a simple problem, and then I will go into, some, stuff, let us see whether we can, we can discretize it. This is 1 and 2, okay. This is only single element discrete. We can discretize it into multiple, right, by putting another, inserting another node, but we are not doing it. So this is what? This is fixed and this is hinge, right? This is fixed and hinge. So what are the, what are the degrees of freedom here? Only 1 degree of freedom, that is only theta here, right? Theta. So if I consider this is node 1, node 2, element 1. So W1 theta 1 will not be, only W2 theta 2, only the last term will be there, right, last term. So let us do that. So we are assuming EI by L cube, and then 4L square, right, 4L square, and then here minus P by 30L L square, this into theta is equal to 0, theta 2 is equal to 0, right. So this must be 0, you see. So essentially only single term, assembly we have done, right, single term assembly, right, because there is only one theta. So theta 2, I am just node 2, that is why theta 2 and theta. So this, when it is 0, then it is 4 EI by L minus, what is this, 2PL by 15 is equal to 0, right. Right. So then Is that fine? So, what you are getting here, you do not require to solve for the eigenvalues because it is only a single term, right, only single term approximation. So, here you will see that P will be what, 4 EI by L multiplied by 15 by 12 na, and then it is so this is 15 by 12, and then it will be 30I by L square. Now, you tell me if it is 30I by L square, what is actually so P critical for this? So, what do for matrix this matrix method or finite element method, I am getting 30I by L square, right? Now, what you get for actually whatever you have learned from your undergraduate course? What you have learned? PCR was pi square EI upon L square. L is how much is L for this one? 0.707, right? Because it is something like this and then it will come like this. So, there is a point of counterflexure. So, this distance was I think around 0.707. I think something like this, right? Because here it will be hugging curvature and then there is a change in curvature. So, this can be this will be a hinge over there, I mean equivalent hinge. So, 0.707 L square, you see how much it is coming? Could you please tell me how much it is coming? I think it will come in 28 something, okay. So, there is little difference, okay. And the difference is because what the finite element is approximate technique, right? And second thing is that finite element make the structure more stiffer, right? Because displacement finite element, displacement is formulation, you are assuming the displacement field, right? So, that makes you, so you are constricting your structure to deform in some way, right? So, that makes the structure stiffer. Displacement is finite element always make the structure stiffer. So, it is making the structure stiffer, that is what you will see maybe little less here, but the error can be reduced by having higher and higher discretization. You can have 2 element, 3 element, and that thereby you can capture higher and higher mode, right. So, you can do more problem, okay. Now, before completing one more important step, I am going to show it to you, okay. See, what is all of you understand what is rigid body mode, right? In finite element, did you check for the rigid body mode? Even in the element stiffness terms, So, a element stiffness matrix, to check that whether it is, it is a legitimate, or not, then you must check for the, the rigid body mode. So, that means, so this is a beam element. What are the two possible modes of there rigid body? One is it is deforming by some amount here. This is a rigid body. So, maybe this is W, this is W. Another rigid body mode, if it is rotating, you are rotating by some amount theta, rotating some amount theta. That means these two fellow will, this will be W L by 2. Here it is minus W L by 2, and here you see that the so it is positive theta, and here it is negative theta minus theta, right? Okay. No, not like that, not negative, not right. If it is like this, that will be same theta, okay, because you have to consider this, sorry for that, okay. How can it be theta, right? So, here you please see what is the displacement, W 0, W 0, right, and what are the displacement component here, minus W L by 2 theta, W L by 2 theta, right. So, both of these are rigid body, right, rigid body deformation, right, rigid body deformation, deformation pattern. So, now you tell me, you have done this thing already in your finite element. I am going to put this same. If you put W 0 W 0, then what is happening? You see this into W, this into 0, this into W, this into 0. This will be 0, right? And then if here you are putting this into W, W into 0, 0, 0. There is no resisting force, no nodal force developed, right? No nodal force developed, right? No nodal force developed, because of course that it should be, because in rigid body deformation there shouldn't be any force developed, right? The force must be developing due to elastic deformation, right? Now you come here. Okay, this is for this one. Okay, what about this one? If we put this one minus WL by 2 theta WL by 2 theta, what is happening? 12 minus WL, you please see that, this and 6L theta minus 6L theta, this will be all 0. Multiply this with this, it will all be 0. So that means in both the rigid body modes it is not developing any nodal for resisting force, but now you come here. So when you are coming here, then what you see, that you see W 0. So then what is happening? This into W, this into 0. Yeah, well, I mean first one is being 0. What about this one? 3L into W, this into 0, minus 3. Well, 0, 0 is coming, not a problem, right? Now, this geometric stiffness matrix, if it acts upon this one, then what is happening? Minus WL by 2 theta, WL by 2 theta, 36 minus WL by 2 3L theta, 36 WL by 2 3L theta. So 3L theta, 3L theta. So 6L theta. Three 6L theta. What about this? Minus 3 WL square by 2, or else this 3L into this and then 4L square. So you will see this, I will just directly write, okay, minus 30 and 30. For the rotation one, you will see P by 30L, and it will be minus 30 theta L, 0, 30 theta L, 0. What does it mean? It is not resulting into 0 forces. There are additional forces that is being developed. So what does it mean? What are the forces developed? This one is minus, here is 30, whatever forces is developed, this one, and then here also this forces is developed, right? These forces, so that means rigid body modes are not shown by the geometric stiffness matrix. These forces are, kick of forces. That means, why it is happening? Why the geometric stiffness matrix is not allowing? Why the geometric stiffness is not allowing the rigid body modes? The reason is that, we are only considering the del W del X square, we have not considered the whole geometric nonlinear term. So there is a inconsistency in geometric compatibility. See, what is happening is that this fellow is not able to determine that, see, when we are considering dw dx square, that means as this because of von Karman nonlinear term, whenever that is del w del x is there, it is basically incorporating it. It is unable to distinguish that whether this is due to rigid body mode or it is due to the elastic mode. You understand? Okay. It is unable to distinguish. However, had the complete geometric stiffness term had been would have been included, then it would have been not showing the, it would have not shown the these kick-off forces. That means the rigid body modes it would have demonstrated. You understand? Oh, it is the truncation of the one term, ad hoc truncation of the one term, that is von Karman nonlinear term out of the whole geometric nonlinear term, that is responsible for that. So, the takeaway is that for unlike that stiffness matrix, the geometric stiffness matrix prevent the rigid body modes. Okay, it does not show the rigid body, at least one rigid body mode. It should have two rigid body mode. One is shown, the pure translation part is shown, but it is not showing for the pure rotation. Why? Because it is unable to distinguish. It is unable to distinguish between the von Karman nonlinear strain and rigid in strain, and then strain due to rigid rotation. Clear? Okay, thank you very much.